Welcome to Homework Lib.
Hi, so over here we're given a reaction in which N₂O is going to be consumed and we're given the values for the frequency factor and the activation energy for the reaction. So the activation factor in this case is going to be equal to A equal to 0.24 times 10 molarity per second. And we're given the activation energy or energy of activation in this case, since it is the common way that it is written down in the equation, that is given as 56.32 kilojoules per mole. So remember that the rate constant for the reaction can be found using the Arrhenius formula, which tells us that the rate constant is equal to the pre-exponential factor or the frequency factor times the exponential of minus activation energy divided by RT. So in the case that we have in hand, we want to know what is the value for the rate constant at 45 degrees Celsius. So at 45 degrees Celsius, this corresponds to, this is going to be equal to 318.15 Kelvin. Remember that we always need to change our temperatures into Kelvin instead of degrees Celsius because that is the thermodynamic quantity. And because in that way, this is going to match up the units of the gas constant, which is 8.314 joules per mole Kelvin. As you can notice in the expression for the activation energy, we need to convert this into joules in order to anything to match up properly. So in this case, the value for our rate constant is going to be equal to 2.24 times 10. In this case, directly 22.4. Here, just a little reminder, in the case that the question was not properly passed down into the numeric system and there's a missing exponent into the frequency factor, please correct for that. In this case, I'm going to solve it as appears on the system, right? So here we have the exponential of 56,320 joules per mole divided by 8.314 joules per mole Kelvin times 318.15 Kelvin. Here, remember to add the minus sign into our expression, so our rate constant at this temperature will be, so the result that we get is 1.27, rounding up to 2 significant figures, times 10 to the minus 8 mole per second. Well, molarity per second. So in this case, the units for our rate constant are going to indicate that we have a zero order reaction. So from the units, we know that this is a zero order reaction. Remember that for a zero order reaction, the units of the rate constant should be in molarity per second. Let me just clean up this a little bit because apparently it started glitching. So, molarity per second, if the reaction is first order, then the units are going to be second to the minus 1. And if it is second order, the units are going to be molarity to the minus 1, seconds to the minus 1. So, for a zero order reaction, the half-life time is equal to 1 over 2 times k, let me get a little bit, times the initial concentration. For example, if we had a second order reaction, the half-life time would be equal to 1 over k times the initial concentration. So we're going to proceed with zero order reaction formula. And we're given that the initial concentration of the reactant is going to be equal to 0.68 molar. So, since we found that the reaction is zero order according to the units of my rate constant, recall that the value for K that we found was 1.27 times 10 to the minus 8 molar over second. And we need to multiply this by the initial concentration, which is 0.68 molar. The half-life time thus becomes 2.677 times 10 to the 7 seconds. So if we convert this into minutes, we simply need to divide by 60, which gives us 4.462 times 10 to the 5 minutes. So now for part B, we are asked how much is going to be spent after 2.75 times 10 minutes when we have an initial amount of 3.25 molar. So in this case, for the zero order reaction, let's remember that the concentration of the species is going to be equal to the initial concentration minus K times T. So for us, the concentration would be equal to 3.25 molar minus my rate constant. In this case, we said that it was 1.27 times 10 to the minus 8 molar per second times my time, which is 2.75 times 10 minutes, which is 27.5 minutes. And we need to convert those minutes to seconds in order to match up the rate constant, right? So we know that in 1 minute, we have 60 seconds. So with this conversion, everything should work fine, and the result that we get for concentration is equal to 3.24998 molar. So over here, what I suspect is that the coefficient corresponding to the exponential on time was not properly appearing on the application, so probably here we're missing an exponent, right? So the only thing that you would need to do is plug that exponent for the correct time that we have here. Same thing goes for the frequency factor on the first part of our calculations. But the procedure should be the same, and you just need to correct for that. That would be all. Thank you very much, and have a good one.